Hello, stats class. This is lesson 9.3c, and we are going to do one more type of significance test in this chapter, and it has to do with analyzing paired data. Can I spell analyzing? I think so. You know what? I just totally messed that up. I'm going to do it again. So paired data, I'm going to remind you of some stuff we did first semester. Seems like such a long time ago, but it's good to review things. In chapter 4, when we were learning how to gather data correctly and do an experiment, one type of experiment we learned about was called the matched pairs design. And so back in that chapter, we learned how to do it, but we haven't learned yet how to analyze data that comes from that type of experiment. That's what we're going to learn today. So in an experiment with matched pairs, basically you give one treatment to each member of the pair. And remember, we're pairing them up based on some characteristic that is similar about them. Or often we do it with repeated measures, which means the same subject gets both treatments. And the idea here is to be able to compare how those treatments work on the same person or on very similar people. Pairs are basically blocks of size 2. And we get them as similar as possible. And back in chapter 4, we talked about some advantages to doing that. You're more likely to detect a difference that way. But what we usually do with this kind of data is we usually subtract the 2 measures for each subject or for each pair. And we end up with a list of differences, which of course are the result of subtraction. So these differences are what we're going to work with. And I just want to talk a little bit about what you would do on your calculator is in list 1, you would have your data from one treatment, or sometimes it's a before and after situation. That's actually pretty common. List 2 would have the data from the other treatment, second treatment. Or sometimes if it's before and after, this would be the after data. And then you subtract them because you're thinking that the second one will come out bigger than the first or something like that. So in list 3, you do the differences. And I'll show you this on my calculator in just a bit when we do the example. Usually it's list 1 minus list 2 or list 2 minus list 1. It could go either way. And we are going to treat this list as the data for the rest of our test. So we're going to do an example of this, the full 4 steps, and I'll talk about the details some more as we go. But let's do an example of a matched pairs t-test. By the way, this is almost always means and not proportions when you're doing matched pairs because you wouldn't be subtracting 2 things if they weren't numbers to start with. So a matched pairs t-test example. Let's do one about caffeine. How does caffeine affect your mood and specifically affect depression? And so this is a typical sort of scientific study that people researching medicine and health and things like that might do. They take a bunch of volunteers, they make them not drink caffeine for a while so that their bodies are clear of it. Half of them get caffeine in a pill, and the half of them, of course, they don't get to be told that they're not having caffeine, so they get a placebo. And this particular study, rather than just do half of each, it was done with a matched pairs design. Repeated measures, each subject actually got both treatments randomly assigned. Or the order was randomly assigned. Got both with a randomly assigned order. You have to have some kind of randomness in there. So some of them got the placebo first and others got the caffeine first. And I think they put like a week in between to let their bodies readjust. Order is what I meant to say. Okay, so randomly assigned order. After they had caffeine pills for a week or whatever it was, then they had to do some kind of a test for their depression. I don't even understand that, but it scores on some kind of depression test. That's depressing in itself, isn't it? And then they waited a week and they did the other, right? All right, so that's a pretty standard setup for this. And so I'm going to walk through the 4 steps, and as I go, I'll show you the calculator tricks and all of that we need to know. So the state is still hypotheses, null hypothesis, and alternate hypothesis. The difference here is that our means are not the means of the original data, it's the means of the differences. So it's called mu d. So I'm going to put that off to the side. Mu d is the mean difference. We're going to use the differences as our data. So the mean difference, we are almost always going to do the null is dull, and that means that our null is going to be that the mean difference is 0. There is no difference. That's our null. It's almost always 0, and you don't need to worry about when it's not, unless you do that for your project or something weird like that. So it's almost always 0 because the null is dull. The mean difference is officially the mean difference between the scores and depression scores. Try not to get depressed about that. And we're going to do placebo minus caffeine because we think that the placebo is going to cause more depression than the caffeine, I guess. So you always have to specify which direction you're subtracting because that will affect your alternate. This placebo minus caffeine, I think that the people who have caffeine will be less depressed because, hey, they're going to be happy with the caffeine. And so we're going to do an alternate of greater than 0. We think that the placebo will cause more depression. So you're always going to set up your alternate based on what you think will be true. And then we're going to do this whole thing at an alpha level of 0.05. Some of you have been forgetting to do the alpha, and actually I totally understand that because I often forget to do the alpha until like later I think, oh yeah, I was supposed to put alpha up there. Try to remember on this next quiz. All right, so alpha is 0.05 as usual. Our plan is we're going to do a t-test. Technically, it is called a paired t-test for a mean difference. You could also call it a matched pairs t-test, and I would understand that. You do need to say somewhere in there either the word paired or the word difference. Those 2 words are the main difference between what we're doing now and what we did in 9.3 A and B. So we're going to check the same 3 conditions as before, except that there's one change that I will tell you about when we get to it. Let's start with random. Here's the first one we've seen that's an example of an experiment instead of a survey. So this is not a random sample of people. These are volunteers, but it is randomly assigned treatments. Remember we said randomly assigned order of treatments, and that is how we get our randomness here. This is how you do it for an experiment. So instead of looking for a random sample, it's just treatments. Normal, now this is interesting because we actually have 3 lists on our calculator. And I have to show you the data before we can go on. So let me just show you the data. If you'd like to put this data in your calculator and work along, you could pause the video and get the data real quick. There's the data. I'm going to put this in list 1 and this in list 2 and show you that for just a minute. In fact, I already did put the 3 lists in there, or 2 lists in there. List 1 is the caffeine depression scores, and list 2 is the placebo. And then list 3 needs to be the differences. Oh, it might help if you could see that, huh? So the differences, I said I was doing placebo minus caffeine, which means I need to do list 2 minus list 1. And that means, so basically I'm doing list 3 is list 2 minus list 1. And you could do that at the very top of your list. List 2 minus list 1. I just did second 2 and second 1 to get that. And that's my list of differences. So the question I have for you is, first of all, there's only 11 subjects in this study, as you may have noticed on the table a second ago. N equals 11 is pretty small. It's less than 30. It's less than 15 also. So what do I need to do? Hopefully somebody would tell me. I need to look at the graph. And the question I have for you is, which graph do you think I would look at? Would I look at list 1 graph, list 2 graph, list 3 graph, or all 3? And you can make your guess before I say it, but basically what you have to do is the graph of the differences is the one that matters, because we're using it as our data. So I do not have to plot list 1 or list 2, only list 3 matters. And I'm going to be a little bit lazy and not do it on my calculator. I'm just going to show you the graphs since they're in the book. This is page 579, by the way, in your book. And there's the graphs. They did a histogram, they did a box plot. They're being overachievers here. And then they did a normal probability plot. And we're looking at this to see, is it too skewed? It's actually a little bit skewed, but not too bad. They called it, actually, I'm going to see what the book says. The book says it's a little bit skewed, but not too terrible. And so we're going to go with it. So that's basically how you check the normal condition for differences. You have to check the graph of the differences. And the plots are a little skewed. The book says they're close enough. I'm going to say proceed with caution because I like saying that. All right, exclamation mark on that. Independent is a little bit different for experiments. For experiments, you don't actually have to check the 10% rule, so I'm going to write that off to the side. No 10% rule for experiments, although I don't think they would mark you down if you did that. You just don't have to. You can say because it was randomly assigned treatments, that makes it independent. Yes, because we have randomly assigned treatments. Got the S on that. So that's a change for experiments. And for matched pairs, that often happens where you just say randomly assigned treatments, therefore I can assume it's independent. Good. Makes it easier to check, actually. Step 3, do. As you might expect, this is going to change a little bit also. So instead of having X bar and mu, now we have everything with a D on it for differences, and we're still going to do a t-test. So we're going to do t equals, it's going to be X bar minus mu over standard deviation over square root of n, except we're going to put D's on everything. So this is an X bar D and a mu D and an SD. And n really doesn't need a D on it, but all of those things are coming from the differences. So X bar D, for instance, is the mean of the differences, which you would get by finding the mean of list 3. SD is the mean, is the sample standard deviation of the differences. So in other words, you don't actually have to do any calculations with list 1 and list 2, except for finding the differences, right? So we're going to find both of these by doing one variable stats on list 3, like this, stat calc, one variable stats, list 3 instead of list 1, and calculate. And that will give us our xd bar, whatever, 7.36, and this is 6.92. And we're going to use those. All right, so my t is 7.36 minus my hypothesized mean was 0. You could leave off the minus 0 if you wanted to, and then I have my 6.92 divided by square root of my sample size, which is 11. By the way, one variable stats tells me that also, just in case I didn't know. And so that comes out to, let's find out, 7.336 divided by 6.92 over square root of 11. And yes, that parenthesis that I put in is important because you want it to divide by this whole thing, not divide by this and then divide by that. And I got 3.53 if I round it correctly. And then I have to find a p-value. We've done that before. P is TCDF. It is a greater than in my alternate, and it's also a bigger than 0 here. So that's good that it came out the same direction. So I have to put my T first, and then 999, and then GF is 10, because remember that's 11 minus 1. So I go second bars, TCDF, not negative 999, but 3.53, and then positive 999, and 10. And that is 0.0027. Really small p-value we're about to reject. That's good. Before I go on, I'm going to remind you that you also could do stat tests and the t-test. So you could do the calculator shortcut in case you forgot. It's a t-test. And the main thing you need to remember is you could type in x bar and mu. By the way, that's a 0. Or x bar and s, I mean. Or you could choose data and tell it to look at list 3, which I think is easier. And it is a greater than, and all of that looks right. So calculate, and it should be the same thing we just got, which it is. That's good. So that's sidetrack. Number 4, conclude. All right, this is going to sound a lot like what we've done. Should be a good review for the quiz, right? Since P is 0.0027 and it's less than 0.05, I hope you already knew that we were rejecting the null that. This part should be kind of automatic. And then here's where you have to start thinking a little bit. You have to think about what was our mean. Our mean is that there is no difference between placebo and caffeine. I'm going to say it that way, that there is no difference in depression scores between placebo, or actually maybe after taking a placebo versus caffeine pill. And so here's a reminder that the null is dull. The null is there's no difference, nothing exciting. The test did not find anything interesting happening. And the alternate is what we're concluding is true. We conclude, and you write a statement about the alternate that says that the difference is greater than 0, that the placebo, people are more depressed on the placebo, or people are less depressed after taking caffeine. That's what we're going to conclude. People who use caffeine are less depressed. Or you could have said the opposite. You could have said that people who use a placebo are more depressed than those who use caffeine. So that's our conclusion. And then we're going to add one more piece because some people missed this on the last quiz and I want to talk about it again. Let's talk about interpreting a p-value, because often you are asked to do that after a test. So the p-value is 0.0027. That's less than a percent. It's 0.27%, but let's talk about what that is. There's a 0.27% chance of what? And if you try to write this before me, you'll learn a little bit more. So pause the video if you want to. It's a 0.727% chance of getting, the part I have memorized is our result or more extreme, except I'm going to write it in context. Our result was a difference of 7.36, a sample mean difference of 7.36 or more extreme. In this case, it's or more because our alternate was a greater than. If the null is true, but I'm translating that statement also, if the null is true, is that there really is no difference. If there really is no difference between caffeine and placebos. So that's interpreting the p-value. And I'm going to stop there, and we will come back and review for the next lesson.